Thank you very much. My name is Teoman. I'm a data scientist at the Next4biz R&D Center. And in this presentation, I will be presenting to you AnomalyNet, our latest anomaly detection project. So before introducing the project, I'd like to start by talking about who we are. So Next4biz is a CRM, CSM, and BPM software development company located here in Istanbul, Turkey. Under the regulation number 5746, our organization is recognized as a research and development center. So our organization provides three distinct platforms. The first one is our CRM platform, which offers things like unified customer management, the CSM platform, which offers features like omnichannel communication, and the BPM platform, which is the main platform this project is related to. So our customers are spread all across the globe with some pretty recognizable brands amongst them. So our BPM platform essentially provides users with the ability to visually design and execute their business process operations and workflows. It also supports third-party integration, so the users can integrate it into their own tools. So before continuing, I'd like to start by explaining what exactly business process anomalies are. So an anomaly within the context of business process management can be defined as any deviation from what is the standard or the norm for a given business process workflow. These deviations can be anything ranging from a simple employee mishap or any fraudulent activity within a given business. So AnomalyNet as a project aims to provide tenants with a framework meant to detect these deviations to help users optimize their workflows and potentially increase their profitability and resource allocation efficiency. So before continuing, I have to acknowledge that this project is supported by the Scientific and Technological Research Council of Turkey under a TADEP grant. So in the AnomalyNet framework currently is in development, and the planned workflow, as shown in the diagram, works by event logs being executed in the BPM platform. They later get stored in the BPM database, which is a tabular database. And then once they are sent to the framework, a graph conversion engine converts them into graph data objects to later store in the Neo4j graph database. Once that is done, the graph neural network, which will act as the brain of the framework, will perform anomaly detection on the event logs. And once that is done, the framework is aimed to provide users with corrective action suggestions. They can be thought of as deep learning model-based evaluations of how to optimize a given workflow. So from the beginning of the project so far, we've done a total of 6 studies published at various international conferences so far. And in this presentation, I will be presenting each one of them in detail. So before I begin presenting them, though, I'd like to first go over some preliminaries and some universal constants across the studies, right? So in the context of business process anomaly detection, the business process event logs consist of 3 main components. The initial one is the attribute, which essentially is every single cell you can see in this sample of dummy data. An event is essentially each row in a given business process trace, and business process trace is a single business process record that consists of multiple events. Each of these components represent a different level of anomaly detection. So for an example, a trace level anomaly detection will refer to as the identification of anomalous traces, whereas attribute level anomaly detection will refer to as anomalous attributes, such as an example, a user not being authorized to perform a given activity. So in the context of business process anomaly detection, there are various perspectives which anomaly detection can be done through. The most commonly researched two perspectives are the control flow perspective and the data perspective. So the control flow perspective essentially focuses on the activity flow. So say for an example, let's say that we swap the places of model training and result validation. This will be detected as a control flow anomaly because it's an anomaly found within the control flow sequence. And the data perspective is essentially any field that is related to the data attributes of the event logs, such as the user ID field there, as an example. So the main reason why we focused on the usage of graph data structure is because business process event logs can naturally be aligned with the graph data structure. So on the diagram currently in the screen, the green box represents a start state, which is the beginning state of a given business process record. The blue states represent the intermediary states, which the business process trace will travel through to reach an end state, where they will be terminated and closed. So the black lines in between the states represent the transitions which the business process trace will travel through. And when we process the states as nodes and the transitions as edges, event log data can naturally fall in line with graph representation, allowing us to do more comprehensive, not only anomaly detection, but also process mining related tasks. And because of that, our studies mainly focus on usage of graph data structure, graph neural networks, and unsupervised methods to detect anomalies. So throughout the studies, we used three data sets. So the initial one is a data set that is extracted from our BPM database. It belongs to a tenant of the Next4biz BPM platform whose identity will be kept anonymous. And the other two data sets are the 2012 and 2017 editions of the Business Process Intelligence Challenge process mining data sets. So these data sets are actually favorites in the process anomaly detection community. They're also some of the most commonly used benchmark data sets. And that's why we prefer to use them. So before I move towards the studies, one thing that we did, which can be said to be universal across all our studies, is the usage of a percentile-based prediction to mimic the real-world usage of such a solution. So, say for an example, on your screen you can see an ordered plot of reconstruction errors, right? So the 99th percentile point essentially represents instances with an anomaly score of 99 and above. 95th percentile. Any data point above the 99th percentile is going to represent an instance with an anomaly score of 95 and above. So this approach actually allowed us to better mimic a real-world use case. But one issue was that, say, for an example, let's say that we took the 99th percentile, labeled everything above it as an anomaly, and then I calculated an F4 score based on that. So even if every single data point above this threshold is a true positive, there's still going to be a lot of true positives below this point, which essentially will make F1 score not very representative of the real performance. So because of this, what we did was we used a custom evaluation metric we refer to as the success rate. So success rate can be formulated as all the true anomalies above a given threshold, the count of all the true positives above a given threshold, divided by the count of all the data points above a given threshold, times 100. And what the success rate does is that it allows us to evaluate threshold score points as separate as a separate benchmark point. So the first study I'd like to present is it's the first study we've done for the development of the framework. So the study focuses on the usage of isolation forest for anomaly detection over business process event logs processed to represent previous, current, and next state subsequences. So we used the isolation forest algorithm with contamination rates of 0.01, 0.05, and 0.1. So once the study was complete, we delivered the findings to the business intelligence specialists we have in our research center. And they were able to validate that the results were, in fact, truly anomalous instances. So following this study, we made a separate study, which was presented at the Innovations and Applications in Intelligent Systems Conference this year. So the following study focuses on the usage of unsupervised graph neural networks with a custom form of automatable semi-supervision, which is meant to be replicable in the production as well. So this study also focuses on the identification of the traces which contain anomalous subsequences as they are defined in the previous study. So the graph construction algorithm we used for this study is an adaptation of what a previous researcher did in 2021. So the initial step in our graph construction algorithm is the initialization of the edge embedding space. So to create our edge positional embeddings, we initially create an empty feature matrix with a dimension size of maximum trace length -1. Once that is done, we pair each state at time t with the state at time t+1 to create our edges. We repeat this through the entire business process trace to get to all of our state-state pairs, which will be our edges. So once that is done, we create our edge positional embeddings by inserting the relevant features into their respective indices within the edge embedding space with respect to their activity order within the trace. So the last step in our graph creation scheme is the aggregation of edge embeddings. And what we do is we aggregate the edge features of each duplicate edge until we have no more duplicates left. We repeat this graph construction algorithm across the entire data set. And once that is done, we acquire our graph data set. So the graph neural network architecture we leveraged in the study is a novel type of graph neural network architecture, which leverages the information found on edges during the decoding process, aiming to increase the reconstruction performance. By doing so, the aim is to achieve a higher anomaly detection performance. So the automated semi-supervision we used is so the initial step we did was to handle the variance in the reconstruction errors. Once that was done, we calculated z-scores for each reconstruction error of each individual trace found in our dataset. And then once the z-scores were calculated, we selected a safe upper bound of median z-score times 2. Once this was done, we picked approximately 60% of the instances within the data set to be unlikely to be anomalous. So the idea here is that after an initial round of training, the autoencoder should detect some anomalies. And we can tell that there are anomalies based on the reconstruction errors. So any instance with a high reconstruction error is going to stay on top. And once we pick a point like this, every single data point below that is either going to be normal or there will be a negligible amount of anomalies below that data point. So the experimental results show us that the applied form of semi-supervision here does actually increase the anomaly detection performance When we look at the 99th percentile point, the fully unsupervised model detected no anomalies above this point, whereas the semi-supervised model detected only anomalies above this point. And then as we progress below, we can see that the scores become very close at the 80th percentile with only a 0.07 difference in F1 score and 0.6, I mean a 6% difference in the success rate. So the data set with the anomalous subsequence labels contained a total of 995 anomalies, and we can also see that the semi-supervised model, even if at the 80th percentile, also was able to detect all the 995 anomalies within the dataset. So in conclusion, we can say that the applied semi-supervision is a good enhancement to the performance of the model. So the next study I'd like to present is one that we presented this year at the International Conference on Computer Science and Engineering held in Athens University this year. So the study focuses on the incorporation of natural language feature vectors into graph-structured business process data. Given their nature, business process event-log data tends to contain plentiful natural language data. Because of this, what we can do is we can get their word vectors and then integrate them into the graph structure to achieve enhanced anomaly detection results. So one thing that was done in this study is that we switched over from using the anomalous subsequence graph labels into using artificially injected anomalies as truth labels. The main reason why we did that was because this was a very common approach when benchmarking business process anomaly detection solutions. So the acquisition of the word vectors go as the following scheme. So the initial step is to feed the relevant language data into a BERT-based encoder. And then once that is done, they're pooled by using a dense layer to get a unidimensional representation of all the natural language features. Once that is done, we apply feature concatenation with the original one-hot encoded feature vectors with the newly acquired word embedding vectors to create a new set of features for the graph structure. So the experimental results in this study actually show that the incorporation of word feature vectors, word embedding vectors, does provide noticeable results. In the tenant dataset on trace level, we see an increase in anomaly detection performance of 0.11, and then at the 2012 dataset, we see a 0.07 increase. The biggest increase in detection performance can be seen at the event level of the 2017 dataset with a performance increase of 0.20, which is the most significant increase we achieved in this study. So the next one I'd like to present to you is one that we also presented at the International Conference on Computer Science and Engineering this year. So this study focuses on doing edge feature reconstruction to detect anomalies which are more relevant to transitions, which are represented as edges. So the study uses Kolmogorov-Arnold networks to enhance the reconstruction process to achieve a higher anomaly detection performance. The study also uses the Next4biz tenant dataset and borrows the previously used graph construction scheme to construct the graphs. So the initial ground truth labels for this dataset were detected by commencing a data analysis study over the dataset. So we focused on three types of anomalies which are more related to the transition. So the initial one is the illegal transitions found within the dataset, which essentially is a transition between two states that should not have occurred. The second type of anomaly we focused on is the overtime anomaly, which essentially is when the duration for a transition is significantly longer than it should be. The last one is the over-repeat transition anomalies, which focuses on the identification of transitions with which are repeated way too frequently in a business process trace. So one novel thing we tested in this study is the usage of dimensionally increasing autoencoders. The idea is that when we increase the dimensionality, we can achieve more feature-rich latent feature representations, but this can also backfire in a way that if the decoder learns to reconstruct the anomalies as well as it can do with the normal instances, what's going to happen is that it's not, even if it shows better reconstruction performance, it's still not going to show great anomaly detection performance. So the graph autoencoder architecture we used uses an edge condition convolution based encoder borrowed from previous studies. So the main specialty of these convolutional operators is that they take dedicated neural networks as one of their parameters, making them great general purpose convolutional operators for edge attributed graphs. And the decoder so we actually had two decoder architectures in the study, one of them an MLP-based baseline decoder and the latter a CON-based decoder to achieve increased reconstruction performance. So the experimental results show us that the CON-based model at all thresholds except the 99th percentile point outperforms its MLP counterpart at all given thresholds. And then when we take a look at the dimension increasing results, however, we can see that the MLP-based graph autoencoder model does outperform its CON-based counterpart, which tells us that the MLP-based model does make better use of the richer information found in increased dimensionality of the latent feature representations. Still, the champion model in the study is the CON decoder-based dimension reducing model. So the next one I'd like to present to you is an expansion of the graph neural network model I've introduced to you in the first study. So this one was presented at the International Artificial Intelligence Data Processing Symposium. So this study focuses on the usage of what we refer to as the Edge Information Decoder. As I've mentioned, in this study, we explored ways to construct this type of decoder with varying convolutional operators as well as experiment with other parameters. So the graph construction scheme in this specific study follows a pretty rudimentary algorithm. We essentially insert the relevant state features into the node feature space, and then we insert the relevant transition features into the edge feature space. And once that is done, we aggregate everything, yielding us the graphs leveraged in the study. So as I've mentioned, the graph autoencoder architecture in the study once again uses the idea of incorporating the information found on edges to improve the reconstruction process, resulting in enhanced anomaly detection performance. So for this study, we used an MLP-based baseline for benchmarking purposes, and then we used three convolutional operators, one of them being the basic graph convolutional operator, the second being the graph attention convolution, which uses an attention mechanism, and then the last convolutional operator we tested with is the edge condition convolutional operator. And as I've mentioned, the main reason why is because it uses dedicated neural networks as parameters. It makes for great general purpose edge convoluting convolutional operator. So the experimental results show us that at least with the graph structure we used in this study, the ECC decoder outperforms all of its counterparts across different data points. We can see that it doubles its closest competitor, which is the GCN-based decoder. And with regards to the encoder performances, we can see that when it comes to the encoding task, the graph attention-based encoder does significantly outperform its ECC-based counterparts, which does show us that the attention mechanism provides a lot more use when encoding the data into meaningful latent feature representations. So the last study I'd like to present is a study we did for the explanations of anomalies using XII methods for graph-structured neural networks. So this one was presented at the Mediterranean Conference on Pattern Recognition and Artificial Intelligence. So this study focuses on the usage of, as I've mentioned, explainable AI methods on graph neural networks. In this study, we tested with various encoder-decoder combinations, as well as, once again, dimension increasing autoencoders. And we benchmarked on artificially injected anomalies here once again. So to explain the root causes of anomalies, we used two different XAI methods meant to work on graphs. So the first one is the GNN explainer, and the latter is the graph line approach. So the initial part in the detection of the anomalies was to, as done in the previous studies, use unsupervised model to do an initial round of anomaly detection. Once that was done, we trained a supervised model to later explain the predictions of. So the encoder architectures we used. So the initial one we used leverages Chebyshev convolutions, which is based on Chebyshev polynomials on graphs. The second one is the graph attention convolution. The third one is the basic graph convolutional operator. And then the last convolutional operator we use to construct encoders. For the encoders, that is the graph sampling and aggregation convolutional operators, each one of them with their own working principles. So the decoders, once again, we used an MLP-based and a CON-based decoder with hidden dimension size ranging from 8 to 512. So we actually picked two champion components here. So throughout the encoders, the Chebyshev convolution-based encoder showed the highest performance in trace level with F1 score of 0.49 at the 95th percentile point. And then with regards to the decoders, the CON-based decoder showed the highest performance with an F1 score of 0.49 once again at the 95th and the 90th percentile points. So the explanations received show us that the graph line puts a lot of negative user importance on the user-related fields, which indicates that depending on the user, it is going to be very unlikely to be an anomaly, whereas depending on certain states and transitions, it will be much, much more likely to be a true anomaly. On the other side, the GNN explainer, which doesn't really yield negative feature importances, show us that the duration is the least important feature across all types of features, whereas the most important one, once again, is the transition-based fields. So for the closing remarks, I'd like to give a special thanks to my research and development team here at the Next4biz Research Center for their helps in the studies. And I'd like to thank everybody for attending to my presentation. And if you have any questions, I'd like to receive them now.